our next example, let's consider the limit as x goes to minus infinity of x squared times e to the x. If we think about these pieces individually, x squared looks like this, and e to the x looks like this. And so as x goes to minus infinity, the first factor goes up to infinity, and the second factor is going towards the x-axis. It's going towards the value of 0. So this is an example of our 0 times infinity indeterminate form. What do we do with 0 times infinity indeterminate form? Well, we use an algebraic property of multiplication and division to rewrite the expression that we're taking the limit of. So I'll leave the x squared in the numerator, and I'll rewrite so that the e to the x is in the denominator. So when I move it to the denominator, that exponent becomes a minus x. When I think about this rewritten limit, as x goes to minus infinity, x squared is still going to infinity. It's still the same graph. But e to the minus x, that's the flip horizontally of e to the x. So that is going to infinity. So now I get an infinity over infinity indeterminate form, which doesn't feel like I've made it any simpler, except that infinity over infinity indeterminate forms allow us to use L'Hopital's rule. So I consider the limit as x goes to minus infinity of the derivative of x squared, 2x, over the derivative of e to the minus x. The derivative of e to something is e to the something times the derivative of the something. So derivative of minus x is minus 1. Well, 2x, that's a line, and minus e to the minus x, that's just flipping e to the minus x, so it looks like this now. As x goes to minus infinity, 2x goes to minus infinity, and minus e to the minus x goes to minus infinity. This is still an infinity over infinity indeterminate form. But if I apply L'Hopital's rule one more time, which I'm allowed to do for infinity over infinity indeterminate forms, the derivative of 2x is 2, and the derivative of e to the minus x is e to the minus x times minus 1, and I still have this factor of minus 1 left. So now I'm looking at the limit as x goes to minus infinity of 2 over e to the minus x, or, bringing that back to the numerator, 2 e to the x. Well, here's our graph of e to the x. As x goes to minus infinity, this function goes to 0, so direct substitution yields 2 times 0, or 0. And that's our final answer for this limit. So when we have a 0 times infinity indeterminate form, we have to rewrite the expression to get it in 0 over 0 or infinity over infinity indeterminate form. And then we're able to apply L'Hopital's rule. This particular example required 2 applications of L'Hopital's rule because we had indeterminate form of infinity over infinity after the first step of L'Hopital's rule. But ultimately, after 2 applications, we were able to get a limit existing, and by L'Hopital's rule, as long as that limit exists, we can follow it backwards to say that the original limit is 0.